and welcome to this session today that we're going to be having on From Chaos to Clarity. If you could message me in the chat if somebody is paying attention, just to let us know that you can see and hear us all correctly today. And we've got a really good session today. We're going to be taking a look at clock domain crossing and what it is, the functionality of it. And then we're going to take a look at a demo using the CDC tool. But first off, we're really privileged to have Dave Wallace here from us, who's a chief scientist, knows an awful lot more about clocks and clock domain crossing than I ever will do. So he's going to give us a presentation in a second. I'm just going to give us a few more house rules. So as we go through this today, please feel free to put any questions that you've got. If you can put them in the questions tab, that would be wonderful. If there's anything you want to put in the chat, of course, put it in the chat. But if you put it in the questions, then we'll make sure that we can at least see it, and we'll try and answer it. Because there's two of us today, what we've got is we've got a little video which is the majority of the presentation, so it's not quite live because we want to make sure it is correct. So we'll keep an eye on the questions and things as we go through, and there is some polls as well that will be popping live as we go through this. So Dave, thank you very much for spending some time and coming to join and talk with us all today. I'm going to start your presentation, and then we can take it from there. And like I say, any questions, any comments, put them in the questions, please.
Hello. As Adam said, I'm Dave Wallace. I'm Chief Scientist of Blue Pearl Software, and we'll be talking today about going from chaos to clarity, how to use CDC methodologies for success in your designs. So first, the chaos. Designs these days use more and more clocks. We see that for both ASICs and FPGAs. For ASICs, 90% of ASICs have multiple clock domains. For FPGAs, it's over 85%. You have multiple clocks running around on the chip, and that means that it becomes more and more important to deal with the interactions between these different clocks and the clock domains that they're part of. And this can wind up producing bugs that can escape into production, and often do if you don't wind up checking for them. So let's see what's going on. They're basically two different types of clock relationships. Clocks can be synchronous to each other. And in this upper diagram, we see right here a buffer, but it could be an inverter. It could be a clock divider. The two clocks here can be running at slightly different rates. The key is, do you know the phase relationship between the different clocks? Do you know how a clock edge on the first side interacts with a clock edge on the second side? If so, you can use static and timing analysis to verify your timing, and everything's good. Groups of synchronous clocks will define a clock domain, where each clock in the domain is synchronous to every other clock. That's the ideal state. But in reality, we have these multiple clocks, and we may not know where they come from, or we may know that they are completely independent. So that's the asynchronous side down below here. In that case, you can't generally use static timing analysis or timing simulation to guarantee the timing correctness of the paths between asynchronous clocks. And sometimes it's a design team judgment call. There may be clocks that are technically synchronous, but where the period in question of the approach of the clock edges is too short or too uncertain to be able to usefully use static timing analysis. So the design team in that case may choose to treat clocks as asynchronous, even if technically they could be synchronous. So what is a clock domain crossing? Basically, it's any time you have data that's sourced in one clock domain and received by another. There may be a logic cloud between them, there may not. But if you can't determine the relationship between these clocks, you can't guarantee that setup and hold time violations don't occur and on that second register. And that can cause various kinds of problems, primarily metastability, but that can lead to data corruption. You can have data values being out of sync. This is something that needs to be addressed. So what do? Well, metastability is the major problem that we're trying to address in CDC analysis. And that's what's shown here on the oscilloscope picture. It's basically if you can't guarantee that the data is arriving outside of that setup and hold window, there's a timing within that window potentially where if the data comes in at just the right time or just the wrong time, if you like to look at it that way, relative to the clock, the output of the flop may actually go metastable. It may assume an intermediate voltage between a logic 0 and a logic 1, and it may stay there for a certain period of time. A metaphor we often use is it's a little bit like flipping a coin. Most of the time you flip a coin, it comes up clearly heads or clearly tails. But every so often, it comes down on edge or nearly on edge. And most of those cases will resolve probably fairly quickly into a clear heads or tails, but sometimes it can dangle there if you hit just the right conditions. And you really don't want this kind of metastability propagating through your circuit because you can't really guarantee the behavior of the gates in your circuit if the inputs are going metastable. Industry reports show that clocking and CDC errors are the #2 cause of respins in designs. So this is a real problem, and it's one that's very hard to detect. Why is it hard? Well, first of all, for a lot of FPGA developers, the CDC analysis may not even be present in your FPGA vendor offering tool sets, or it may only run during place and route at the very end of the design. I'll talk a little bit later about why that's a problem. But it depends on the precise timing of the receiving clock versus the data. And for some cases, like RTL simulation, you don't even have that. You only have cycle accurate timing. But even timing simulation doesn't know that phase relationship between asynchronous clocks if they truly are asynchronous. And you just can't time the paths without some sort of bounds on that phase relationship. So what do we do? Well, that's where CDC analysis comes in. And there's a point here that we want to note is that CDC analysis generally uses a different default assumption in terms of whether clocks are synchronous or asynchronous. For static timing, a lot of the existing timing representations assume synchronous clocks by default because they come out of this static timing analysis or synthesis world. Certainly SDC does. So in this case, static timing analysis assumes initially that all paths can be timed. And it's just that you go in and you say, okay, well, these particular clocks are asynchronous. You can't trust any, timing value that we tell you about those. So let's declare those as asynchronous so that the tool will shut up about them because you can't really rely on those timing values. And that's why static timing analysis assumes that clocks are synchronous by default. CDC analysis, on the other hand, is focused on what's going on with the asynchronous clocks. Are the paths between asynchronous clocks properly synchronized or not? And in this case, you basically want to know about cases where clocks might be asynchronous. You don't want to have the clocks be synchronous by default because that would shut the tool up about things that could later be a real problem. And in general, we don't want the default in either case to silently suppress possible error. It's one thing if you have somebody actually look at it and say, yes, this clock is asynchronous, these clocks are asynchronous, these clocks are synchronous, but you don't want to introduce a clock and have it have your tool have default assumptions that will lead it to be silent about real errors in your design that can later trap you. CDC analysis also has to look at the external environment. It's not just paths within the design or on chip, if you're looking at a whole chip, that you have to worry about, but it's the interaction with the external environment. You have paths coming in to the inputs of your design that originate on some clock. You have paths going out that are being received on potentially some other clock. You have to worry about some of these clocks may be virtual clocks because they don't appear in your design itself. It's originating from some clock that's completely off chip and that you never see. So you have to deal with that, making sure that external IOs know what they have, dealing with resets and trying to figure out what you know about when those resets originate or if there are any constraints on those resets. So what do we have to do to set up for CDC analysis? First of all, as much as possible, you want to define associated clocks for the IOs so that you can tell the tool as much as you can about what you already know about what clock domains the signals coming in are related to and going out. We also need to determine which clocks are synchronous to each other. Now, that's where a clock interaction diagram can help you group synchronous clocks into domains. And that's what we see in this diagram on the right here. Each of these ovals is a clock, and the boxes indicate domains where the clocks have a synchronous relationship to each other. The annotation, each arc here is potentially an interaction between two clocks. It says, okay, we've got one or more paths originating from this clock and being received by this other clock. And the annotations on the arcs tell us how many of those paths are already synchronized or not, synchronized or unsynchronized, as well as some other information. Now, we notice some things about this diagram in these annotations here. For example, the interaction between this top clock here, clock I, and IWE clock I down here, you notice that coming in, we've got 9 interaction paths, all of which are unsynchronized, and we have 72 paths coming back, all but one of which are unsynchronized. There's one synchronizer in all those paths. Now that suggests that whoever designed this logic either didn't know or care about synchronization, or maybe was thinking of these two clocks as being synchronous to each other, so he didn't need to worry about synchronization. So that suggests that maybe these two domains should be merged, that this clock should really be part of this clock I group here. At least it's something that you want to investigate and look at more closely. So this is a diagram that can help you figure out what the synchronous relationships are between the clocks in your design. So what do we do to synchronize between designs? So we have some various techniques here, things like double multi-register synchronization, a whole bunch of strategies that we use for synchronizing buses, which are more complex than that, and techniques for controlling reconvergence between signals. But there's another technique which can be used in some cases. If you have, if the surrounding circuitry in particular has control of the receiving clock and can shut it off, then you can guarantee that there's no metastability if the data is only changing at a time when the receiving clock is shut off. And then you restore the receiving clock and everything should be fine. So in some of those cases, you can actually prevent metastability altogether. Again, that's a choice on behalf of the user. So let's talk, first of all, the very simplest is double register synchronization. And the idea here is you just add a second register after the main receiving register. So, of course, if these clock 1 and clock 2 are asynchronous, this first register, the first clock 2 register may, in fact, go metastable. But most of the time, it won't stay in that metastable state for very long. And hopefully it is resolved by the time the second register clocks a value in, and then you get a normal value coming out. If you had a probability 1 over p of the setup and hold violation on the first register, the probability that you get metastability out of the 2 registers is more like proportional to 1 over p squared. And since, p is or 1 over p is a pretty small value to begin with, 1 over p squared is a much smaller value of much larger mean time between failures and such, and that may be perfectly acceptable. In some cases, people may want to add a third or additional registers to make sure of it. But in general, if this register does go metastable, and eventually resolves, you can't tell whether the output was from the cycle n or cycle n plus 1. It's one of the two. The data was changing, but you may have to wait a cycle before you can be sure that you're getting the new value. This technique is ideal for synchronizing single bit values. And although I've shown it here as 2 separate registers being used to synchronize, you can also just use consecutive bits of a shift register and synchronize it all within a single shift register. So that works beautifully for single bits. But what about buses? Let's take a look. Buses need better synchronization. And the problem is that if you happen to hit that metastability on the first clock 2 register here, in a bus, each bit that is changing resolves metastability separately. The coin is landing nearly on edge and it's resolving heads or tails. Well, if you get all heads or all tails, you're lucky. But you do have a very significant risk that, say, bit 0 may get the value from cycle n, while bit m gets the value from cycle n plus 1. Now, that actually works if only 1 bit per cycle is transitioning at a time, if the input is gray-coded. And we'll talk about that a little bit later here. But in general, so for example, if this is going from an integer 2 to an integer 3, everything's fine because only one bit changes on that particular transition. You'll either get a 2 or a 3 coming out. But if you were transitioning from a 3 to a 4 binary values, then all 3 bits are changing. Any of those bits can be resolved either way. So you cannot get out not just a 3 or a 4, but you could get out a 0, you could get out a 7, a 6. And if these bits are representing, say, the state of a state register over on the clock 1 side, you can get a completely invalid state or a state that's completely irrelevant to what the original state machine is actually doing. So this is a real problem. You don't want that to happen. So let's talk about some of the strategies for synchronizing buses. One very common strategy for synchronizing a bus is muck synchronization, where you basically, the receiving side says, I'm not even going to look at this data until you tell me that it's stable and safe. And we use a separate control signal here that is synchronized from the source domain that's synchronized into the receiving domain to tell us when it is safe to look at the bus, when you know that it's not changing. Now, obviously, there's some caveats here. You need to make sure that that control signal goes away far enough in advance of when the data is going to start changing again, that you have time to get through that synchronization and say, okay, I'm stopped looking at the data. It's also possible to do things like do a full handshake here, where the receiving side will send back a signal and say, okay, I've looked at the data, I've stopped looking at it, you can send me a new data. There are a number of different protocols that one can use in those situations, but this is a very, very common way of synchronizing a bus to make sure that the values are internally consistent. So another approach, very common in FPGA design, is to use one of the built-in FIFOs from the library of whatever technology you're using. The FIFOs are generally designed so that they're prepared to synchronize between the write clock and the read clock on the FIFO. And these are very helpful, of course, if you know that the data rates are differing on the two sides. So you can buffer some data in between if the input's briefly providing more data than the output side can hold. And it can look at it on its own time. So this is also a very valid approach. And again, if you know that the input is, or can prove that the input is gray coded, then you know that the standard double register synchronization is safe to use for this bus. And we do, in fact, have some checks that use formal analysis to analyze the logic feeding into this input on the clock 1 side to say, hey, can I prove that only 1 bit changes in a given cycle? At most 1 bit changes in a given cycle. And if I can do that, then I know that this double register synchronization is safe. Or the formal analysis can go back and say, no, I know that 2 bits can change, and here's the circumstance under which they change. And so now you need to use a different synchronization method or figure out how you're going to adjust the logic that creates that. So related to this is the question about synchronization reconvergence. So you may have a situation where a single bit is synchronized into the receiving domain in more than one place. Now that can be fine if basically never the twain do meet. Each cluster of logic would go ahead and use its value and process whatever it's doing independently. But if they can reconverge downstream, and this may be multiple cycles later, you have a problem because, again, if you got metastability in both synchronizers, one may resolve to a 0 while the other resolves to a 1. And these two things are supposed to be the same value. So when you come together later in the logic cloud, you have inconsistent values. You may get a result out that you don't expect because of this metastability resolution. So this is very similar to the interbus incoherence problem we just talked about, but it's a case of, in this case, 2 bits, a bit being synchronized multiple times, or a bit being synchronized multiple times, or maybe 2 related bits where the values are related to one another. And again, you get inconsistent results. You have to be aware of this. This is, again, is something you can check for. So what about intellectual property? Typically these days, people don't design everything on the chip all by themselves. They're using blocks of IP that come from other places, third parties and so forth. So you want to be able to do your CDC analysis of the part of the design you're working on and know what are the requirements of the IP that you're using. If you, on the inputs, what clock is the IP expecting that data to be originating from? Or does it have internal synchronization that can say it doesn't matter what clock it's originating from, I'm going to synchronize it internally? Likewise, on the output side, what clock is that data originating from, so that you can check it against the surrounding circuitry. So this is something where we have some technology called user gray cell, which annotates these black boxes with what's essentially a model of the outer ring of logic up to the registers and such, and will tell you, or will tell the CDC analysis, okay, this data here is expecting this particular clock. This data over here is originating for this particular clock. Here's some feed-throughs that just feed through combinatorially that you need to know pass the data just straight through, so that we can model these cells even without knowing the full extent of the design, which you may not know. If you do have all the detail of your IP, okay, fine, you can analyze it with the rest of your circuit. But often the vendor may not provide that. They may just provide a description or an outer shell of what's available. And things like the user gray cell allow you to do your CDC analysis and check your assumptions about what clocks things are originating from and being received on. One important point I want to note here is that when we fix CDCI violations by introducing synchronizers, we are changing the design. And this can affect, the timing of your signals, the latency particularly, and the throughput. So you don't want to wait to the last minute to fix your CDC problems. If you get all the way through, you're getting ready for tape out, you discover you have CDC problems, you need to introduce some synchronizers. Now you've changed the timing and the latency and so forth, and that invalidates potentially a whole bunch of your prior simulation. So you want to start the CDC analysis at the RTL level, or if possible, to be able to fix and find your violations early before you've invested a lot of time in simulation synthesis and so forth. So there is a new standard coming out that we have been participating in at Blue Pearl. This is from the Accelera Systems Initiative, a cooperative between multiple companies. And the goal here is to try and drive interoperability between vendor tools, so that if somebody doing IP design uses one tool to do their CDC analysis, you can use the output from that CDC in analysis in a CDC of the larger design and have the information standardized in a way that the two tools can cooperate. This is a initiative that's addressing clock domain crossings, also reset domain crossings, which I'll talk about in a moment, glitches and so forth. Blue Pearl has been a member of this working group from the beginning. Our main focus, driven by what our customers need, is for now on CDC, but we're obviously tracking what's going on the rest of this. And if you want to see what's going on with the draft initiative, there are various public comment drafts that you can get at this website here. The latest one that's currently on the website is the 0.3 version of the standard from last summer. We will be coming out with the 0.5 version, which has some significant changes in it, and that'll probably be in the next couple months. So if you haven't spent time looking at the standard, you might want to wait and take a look at the 0.5 version when it opens up for public comments. But you can see that and a bunch of other draft standards there at this particular location. So let me just have a little word about reset domain crossings, because metastability can also occur if you have asynchronous resets on your DFS. It's not just the data input coming in you have to worry about. You potentially have to worry about asynchronous resets and how they're getting used. This can be either on, you can get unsynchronized metastability coming out either on reset assertion or deassertion. Often reset assertion, if it's like a system reset, isn't as big a concern because everything's getting reset. But we do check for both of these, and in particular, you ideally want the release of that reset to be synchronized with the clock of whatever register it is that is coming out of reset, so that you don't get metastability, or if you do, at least that metastability gets synchronized. Now, there is a bunch of stuff in the Accelera standard in that where it's talking about reset domain crossings that's really driven by the needs of these sort of very high density ASIC SoCs and multi-system chips, where they have very complex reset schemes. Typically, we have not seen these as much in FPGAs, and the vast majority of our customers are FPGA designers, easily 95% or more. And it turns out that you know, one of the reasons this is not as big a concern is if you're using SRAM-based FPGAs, which would be, you know, Xilinx, Intel Altera, well, a lot of Lattice designs, maybe some others. Typically, a lot of these issues get handled for you during the configuration of the chip on power on. You know, it will the chip gets isolated from the rest of the circuitry. It comes up, the registers all come up in a known state, and so you with these large SRAM-based FPGAs, a lot of the big issues that are affecting some of the really complex reset schemes that some of the IP designers and you know, system integrators are using that are driving some of the stuff in the RDC standard are typically not as much a concern. They might be a concern for some of the other FPGAs that don't have that configuration phase when you integrate with larger systems. We're trying to track this and certainly track requests from our customers that let us know. But for now, we really haven't seen much of these big complex reset schemes in the designs that our customers are using. So our main focus right now is on the CDC analysis, but obviously we're tracking what's going on with the rest of the standard and want to be able to support that at the time when that becomes relevant to our customers. So the Blue Pearl Visual Verification Suite is one tool that can help provide clarity to CDC, particularly for FPGA designers. We include RTL level CDC analysis early in the design cycle, so you can fix your CDC problems before you invest a lot of time in synthesis and simulation. We have our advanced clock environment, which helps set up the clock groups for CDC. That's where that diagram I showed you earlier came from. We have user gray cell models for many FPGA vendor library IP cells for the libraries that we support. They help you use accurate CDC for that. You can also use the user gray cells for your own IP or for third-party IP that hasn't been characterized. You can work with the supplier of that IP to see if they can provide a user gray cell for you on that. And we do graphical debug of CDC issues with generic hardware schematics. And of course, we are tracking what's going on with the Accelera standard. We've, as I said, been part of that from the beginning. Our intent is to be able to support certainly the CDC features as we're rolling them out one at a time, and obviously track what's going on with the rest of the standard and support that as it becomes relevant to our customers. But we also have many other linting and design rule checks. Again, the intent of our tool is to be able to catch design errors early in the design cycle so that you're spending your time in synthesis and simulation on things that are, you know, that don't have CDC errors in them and can be able to, you know, proceed to higher value of your simulation efforts rather than having to respin that all the time. We also do things like FSM analysis and false and multi-cycle path analysis and STC generation. Again, wherever we can add value early in the design cycle to help you get to your design closure as quickly as possible. And I believe Adam has a demo, which we are going to go to, and then we'll have a Q&A session after that.
Thank you very much, Dave. I thought that was a really interesting discussion and introduction to clock domain crossing, what it is, the challenges that we face. I really loved the description about tossing a coin and what, you know, whether metastability being when it lands on the edges, being landing on a heads or tails. And it's also a great point, actually, and it's true in many engineering issues that, you know, the sooner, the earlier that you find an issue that you can correct for it, obviously the better that is. So I'm going to run you through a quick demo now of how we can use Blue Pearl's Visual Verification Suite to find CDCs in our design. To do that, we're going to use one of the built-in example designs, and we're going to use a design that's going to help us showcase not only the user created or accidentally introduced CDCs, but also CDCs that might be introduced when we're working with IP and how we can verify that. So for those that have never seen Blue Pearl's Visual Verification Suite before, This is what it looks like. Down here we have the file view, and this is the transcript area. And as we go through this, we're going to open several windows and take a look at the design. Now, Blue Pearl works in two ways. The first is it works in a load phase. During that load phase, it loads in your Verilog or your VHDL files, checks for completion against the language reference manual, and it also has the capability to do, as Dave mentioned, to do advanced linting and structural analysis on your RTL. I'll show you a little bit of those checks. You know, for example, those checks that we can do here, they're all disabled because this is a CDC run at the moment. But if we were, for example, to reset them to the default, take a look under the bad logic ones, you know, we can see things such as we can analyze the RTL to see whether there is latches being created or things like that, or whether flip-flops are reset or not reset. If like linting and structural analysis is something of interest, then we can always do another webinar and take a look at that there. What we're going to do now for this example is we're going to make sure that we've got the correct vendor option enabled. So we're going to enable support for AMD Xilinx library support. And we're going to click OK. We've then got two files. So we have the file here, which is a AMD FIFO, and this is written in Verilog, so you can see it pulls in the FIFO generator. So it's using a standard IP-based approach to implementing that FIFO. Of course, because this is doing clock domain crossing, it is a asynchronous FIFO. Then on top of that, we have the actual RTL module, which instantiates that FIFO and which controls the writing and the reading of data from it. And it's this that we want to check is working correctly for clock domain crossing. So what we'll do, the first thing we'll do is we'll click on load design. And during this load design, it's going to load in the VHDL Verilog. It's going to check against the language reference manuals to make sure that syntactically the language is correct. It's then going to apply any RTL and any structural analysis checks that have been applied to it and generate any warnings. One of the things that it's going to do when it's done this, and I'm going to show you the importance of this gray cell, is as it's done that load, it's created a simple elaborated view of the design, which we can see in the schematic viewer. So here at the top level, we can see the drive logic for the reading and writing from the FIFO, and of course over here we can see the FIFO itself. Well, actually, in this case, it's the instantiation of the FIFO, but we can see that. If we expand this, what we will see is the FIFO generator, so the FIFO generator in the FIFO file. And if we expand this further, then we get a really good point about the grey cells that Dave talked about and how they help us work with IP and validating the IP in the design. So we can see here we have the FIFO. Obviously, we want to be able to know what clocks the inputs are associated with and what clocks the outputs are associated with. So to help do the CDC analysis, when the model's been created in Synthesis, what it's done is it has created this grey cell, and for all of the inputs, it's associated a FIFO. If we scroll down to that, we can see for the inputs, it's associated a FIFO with the relevant input signal and the relevant clock. And it's done the same for the output. So it's put a flip-flop in there for the relevant output signal and the clock. Knowing the input and output flip-flops, knowing the clock domains, the clocks that are associated with those signals that go into those flip-flops, means that Blue Pearl is able to do a CDC that includes the IP in the design. Obviously, it doesn't care about the logic that's in between that first rank of flip-flops and that output rank of flip-flops, because we're not doing simulation or synthesis or anything. We're just doing a simple CDC check. So once we've done this, we can close this now. I don't need to use this to explain it anymore. But one thing to further show you is the advanced clocking environment, which becomes available once we have done that loading. And this, as Dave said, is the environment that we use to set up and ensure that our clock domains are described correctly before we go on and do our CDC analysis. So in this instance, anything that is a square is a clock domain. Anything that is an oval is a clock within that clock domain. So we can see we have two clock domains, and we could see this from the RTL that we looked at earlier on. We've got clock 1, clock 2, and it's done a quick and simple look at the clock domain crossing between the two of them. So from group 1 to group 2, there's 2 synchronized, 2 unsynchronized. From group 2 to group 1, there's 0 synchronized and 1 unsynchronized. Now, if we wanted to, we could probably spend quite a lot of time in this view and see what's going off, but it's actually better to do the next stage, which is, because the design's loaded, is to do the analysis view. So if we come over here to our analysis options, just like for our design load options, we can select which check we want to do. So we're going to check the clock domain crossing check. We can come to the CDC options and we can configure the CDC to be run how we want it to do. The main thing, because this is an IP block that sits in the design, we don't want to do the input and output port IO checking yet. If this was a complete design, then yes, we would want to do that. But for the time being, we don't want to do that. We just want to look at what's going off within the design there. So we'll click OK on that, and then we will run the CDC analysis. So as this CDC analysis is run, you'll see it's loading in. It does the analysis on the design, and it's actually pretty quick to run through and do that analysis. What we'll see once it's completed is our clock domain crossing viewer becomes available, so we can click on that and it will open this new view. In this new view, we can see at the moment by default, we can see any of the synchronization types which has failed. If we want to see all of the CDC types, then we can just uncheck this module and we can look at the CDCs that have been detected and analyzed and marked as being safe during that initial cross. So for example, here we can see some synchronization, a two-stage synchronizer going off. We can see some register synchronization, and again we can see some FIFO synchronization of the main data. So if we tick that off for a minute, what's of interest though is the failing paths. And in this instance, the first instance, what we can see is we have some data, 385 bits. It's associated with clock 1. We have a result from the multiplication, and that's associated with clock 2. And in between, there is no clock domain. There is no clock domain crossing logic to help do that. So for example, to safely transfer data into this multiplier result here, we would need some FIFO perhaps, or some handshake synchronizer because it's a bus. If we click on this, we can cross probe to the RTL and take a look at what's going off in the RTL to help us fault find or think about how we might want to change our design. But as Dave said in his talk about it, again, when we introduce this, we're making changes to the RTL. So if we've done lots of verification and validation before we get to this point, then we've got to rerun that to make sure that we've not broken anything and that the knock-on effect is not significant. So we want to do this as early as we can in the design, just like finding any issue in the engineering side of things. The next issue is actually really interesting because it shows that the designers put the FIFO in to do the clock domain crossing and transfer the data correctly. And as we saw, the tool says, yep, you're moving the data correctly using the FIFO. However, what we see here is a slight issue in how that FIFO has been instantiated and worked with. So obviously the FIFOs have full signals, empty signals to help you control the flow of data into and out of that FIFO. And what's happening here is the request data, this flip-flop here, the request data, is clocked by clock 1, which is the right clock in the FIFO. And it's using the signal coming from the empty signal. Okay, there's a little bit of logic down here, but it's using the empty signal to request more data. Now, unfortunately, that empty signal, as you can see, is associated with the read clock. So while the engineer's done the correct job at putting the FIFO in there to transfer data using a FIFO, inadvertently, when they've mapped the FIFO into the design, they've accidentally introduced a new clock domain crossing issue from the read clock domain to the write clock domain by using the empty signal instead of using the full signal to request more data from the FIFO. So this is a really important point, and this is a really nice point because the first example shows how you can detect and find coding issues that people make while they're doing code. This issue actually identifies an example where we're working with IP and the IP's incorrectly being connected up. And in that incorrectly connected up, it's introduced a CDC issue. And because of this grey cell technology, as we were talking about, and as I showed you in the schematic element, it's showing that that there's a inadvertent clock domain crossing, which we need to go away and correct. But again, we can correct it relatively easily. But again, it changes the functionality. So if you're changing the functionality, you've got to go back and rerun a regression suite of tests. So this brings me to the end of my relatively quick demonstration. We have a little bit of time left. So what I'd like to do now is I'd like to open the floor. And if you have any questions to ask Dave on his presentations or me on my demonstration, or any suggestions for future topics for future webinars or topics around this area, then please reach out and let us know. Okay. So hopefully that made a lot of sense to people as we worked through as Dave worked through his presentation and gave a great talk about CDC, what it is, how we can avoid it, how we can work with it, and then obviously I showcased the Blue Pearl visual verification suite tool. Throughout this webinar, actually, people have been asking questions in the questions window, so we've got a little bit of time left. Like all these things, sometimes it takes an hour, sometimes it doesn't. So, but actually, we've got quite a lot of questions in the question chat. So please think of questions to pop them in there if you've got any, and I'll ask Dave some questions. I'll select some of these questions, and I'll ask Dave, and then Dave can hopefully help us through them. So the first two we had from actually was asked a couple of times, Dave, about the clock interaction diagram that you showed in your ACE slides.
Mm-hmm. Yes, absolutely.
Auto-generated, or whether you'd spent hours drawing that by hand.
No, indeed, that's an output from ACE, our advanced clock environment, which is part of the visual verification suite. You get it for free if you're getting our CDC tool, but we've also looked at licensing that separately. There was some interest when we first showed it off at DAC, and we looked at the possibility of licensing it cheaply as a standalone if people were interested in using it to generate clock domains for possibly other tools. We didn't get enough user feedback on that at the time to do that actively, but we could certainly talk to you about it if you're interested in doing that, whether you want to. But yeah, as I said, it comes for free if you get our CDC license. So yeah, that's part of the initial thing, and part of what it can do, if you want it to, is go in and regroup domains based on the percentage of synchronization that it sees already there. Again, that synchronization is just a quick and dirty CDC. It's not the full CDC that you do to get all the messages and so forth. But again, using the idea that if you think that most of the crossings are correctly synchronized or not based on whether the clocks are synchronous, and you're really just looking for a few exceptions, then that might give you a better starting point than whatever you otherwise started with. And the tool does have the capability to do that if you want it to do so.
Cool. Right. Well, let's move on to ask the next question. So on slide 13, you showed there was a question about, couldn't you use the sync bit to act as an enable to the register that latches the data?
And the answer is absolutely. The MUX synchronizer there is basically acting as an enable on the following register, and that's just a feature of the generic hardware that we're synthesizing into there for purposes of analysis. But if you're using a register that has an enable on it, you absolutely could run that sync bit into that
enable bit and synchronize that way. Absolutely. It's effectively the same thing.
Excellent. So somebody else asked, I think this is a relatively straightforward question, but I'll ask it anyway. So somebody else asked about using the difference between using synchronous or asynchronous FIFOs. Is there a pro or con for them? I think generally, and you can expand on this obviously, I think generally when we're doing clock domain crossing, we should be using asynchronous FIFOs, but I'll let you answer that.
Yeah, I think it very much depends on what, typically you're using vendor IP from their library, whatever that vendor IP is, and whether it's synchronous or asynchronous. If it's asynchronous and it's using some sort of handshake, then that would be similar to that muck synchronization that we saw in that one slide. But basically, it's a question of what does the vendor actually supply, or if you're using independent IP that's coming from some other source, you can try and model that with user graces as such. And again, we can try and work with you on that to make sure that whatever you're using is meeting your needs.
Okay. So the next, so we've done that one, that, and that one. So this one's question I'm not too familiar with. Maybe other people are on the call about, and I think you touched on it a little bit, but saying, are there any UVM-based verification strategies for CDC domains, and can they detect CDC problems in simulation? I think it's quite difficult to detect CDC in simulation because you've got to ask exactly the right questions and you've got to have the right timing information and everything like that.
It is detect. I mean, in one sense, internally, yes, we use a form of generic simulation, not specific data value based, but abstract simulation in order to run the CDC. But in general, your simulator that's looking at specific inputs and such isn't necessarily going to be able to pick up on the metastability problem. For asynchronous clocks. But in terms of UVM, I will say that the Acceler group is very definitely looking at UVM, and that's one of the things the formatting group in particular I think is looking at in terms of compatibility and so forth. So there may be some responses coming out of the Acceler standard as we get closer to the official release of that. I can't say specifically what they're doing, but I know that they are looking at things like that in terms of trying to be compatible with what other people are doing out there.
Excellent. That makes a lot of sense. So there's another question. Actually, I think I can probably handle this. So someone's asking about how do they, are there any good examples for open source references or to practice CDC techniques? And obviously, we talked a little bit about this when we were talking about it, and we never quite put it into the slides. But the vendors do provide some tools that will do this for you, such as the Xilinx parameterized macros that will give you the CDC structures that Dave talked about. There's an open logic library that's on GitHub that's got similar things that are device independent, shall we say, if you don't want to be tied to a particular vendor. But they're a good place to take a look at. And of course, as well, if you sort of at the end of this, everyone's going to get an email that's going to say, here, go watch the recording, and it's going to include a link if you want to go and request a trial version of Blue Pill to take a look at. So if you want to do that, and you can use some of the demos and some of the examples in there to learn a little bit more about CDC and how those are crossed as well.
Right. We have a whole bunch of examples and tutorials built into the tool that you can use to learn the various features of the tool, and those all come with their associated source code and such. So you can certainly just learn an awful lot about the capabilities of the tool just working through those tutorials and examples. And I will also note that on the open source stuff, that we use a bunch of that stuff in our regression tests as well. So, there's certainly examples from that out there in the world.
So there's a really interesting question actually just popped in the top, which is about synchronizer chains and saying, does the synchronizer chain require that the two clocks have the same period?
Okay, so let me see that. I just looked up in the list here, and there's one other question I wanted to ask about. Will there be updates, tutorials at DVCon in February from the CDC working group? And I believe that the group is planning to be there to do some sort of presentation. I don't know off the top of my head exactly what is in there, but we've been there at the previous DVCon. We've been at doing presentations at DVCon in Europe and in Asia, I believe. So yeah, definitely, it's likely that there'll be some update at DVCon. I just don't know the answer right off the top of my head on that one. So let's see, synchronizer chain require that the two clocks have the same period? No, it does not. Now, obviously, yeah, and we do things like, flag slow to fast, clock crossings and things like that as well. But yeah, the idea is, if metastability happens, do you have the synchronizer chain to control it? And if so, we say, okay, good, that clock is synchronized. You do have, obviously, if the clocks are operating at different rates, you might very well want a FIFO in there to be able to catch the overflow or underflow, as the case may be. But the synchronization itself doesn't require that they have the same period, and we make no assumption about that. So that's the quick answer.
Excellent. So there's a great question in there about in the Vivado tool, in order to do CDC, we have to add additional constraints like false path, multi-cycle path constraints. Does the CDC analysis tool help generate these constraints?
Let's see, false path. So yes, there is, in fact, you can get a SDC license for Visual Verification Suite, which enables the false and multi-cycle path generation capabilities. And we do generate SDC that has such constraints as we find them. So I think that's the it doesn't come directly out of the CDC analysis, but it is another part of the tool that you can get a license for and can use.
Excellent. So we've got questions still coming in. There's one just popped in chat actually, right at the bottom, that I just want to cover just before it goes away, Dave. And are there any? Yeah. So if we're going so typically we might go from a slow domain to a fast domain, but somebody's just raised a question and said, what about if we go from if we go from a fast to a slow domain, that's relatively easy. But if we go from a slow domain to a fast domain and do cross domain crossing, are there any particular additional caveats that are needed to do that?
Not really. I mean, obviously, if you're going from slow to fast, then not every receiving cycle will get a new value. But the main concern there is just to catch the metastability if it happens, whenever it does transition, and then the receiving side will reflect the new value either that cycle or the next cycle. Going the other way, fast to slow, you have to worry about the possibility of dropping data on the floor, of course. And that's where a FIFO or something might be most appropriate.
Yeah, and there are structures as well. I know we were talking about the open source libraries and the XPM libraries. Those structures do have some pulse transfer information as well about that. I guess for the other thing for slow to fast is you have to make sure you don't overflow the FIFO or anything like that. At some point you've got to be able to read out the data that's being written into it. In terms of questions, let's take a look. There's a few more coming into there. Somebody wants to know if the tool is available on Linux, or is it just on...
Yes, absolutely. It's on both Windows and Linux, so and has been for years.
So somebody, I think this is a great one at the top, actually. So a follow-up question on the two clocks of the same period. Do we need CDC techniques for two clocks, which are the same period but different phases?
I mean, again, that mostly depends on what you know about the phase relationship. If it's a known phase relationship and they have the same period, then you can theoretically use static timing analysis to verify. If you know how close those two clocks are together, you can verify that path. Now, if that approach is too close to be able to have a useful path, you might want to be able to treat them as asynchronous. So that would be a user call.
What about if we came from different oscillators?
I'm sorry, different oscillators?
Different oscillators or different sources where you can't guarantee that they're in their own phase all the time.
Yeah. If you don't know anything about the phase relationship, then you have to treat them as asynchronous. If you know something and can bound that phase relationship, then it may be more of a judgment call. So a lot of it depends on what you actually know about the relationship of those two clocks, and whether or not you can bound that within sufficient safety margins and things like that.
So if you've not voted already, please vote in the polls that we've put up there, because I'm just really curious as to the answers. But I think we've gone through most of the questions now. So if anybody's got any last minute questions before we wrap up, please just pop them in the questions and we'll get to them. Once again, we'll make this recording available. You'll get a link to be able to come and see it. It'll be on my website as well, and there'll be a link to the YouTube channel. We'll make the slides available as well. I don't know how to do that linking from the on demand, but I'll link them with the YouTube. I'll link them with the YouTube channel, such that people can go back and see the slides.
Yeah. And let me just jump in with one more question here. Somebody who had done a Google search about ACE and was asking if it's available for the latest CDC standard from Accelera. The answer is we are rolling out support for the various CDC features in the oncoming standard, but it's not all there yet. So basically, we're trying to prioritize them and put out the features our users need as appropriate. So our future direction is to be able to support the standard, but in terms of what's there today, we've added some capability that will be needed to support the standard. We're still working on the rest of it. So does it work for SDC created clock groups as well? Absolutely, yes. In fact, that's one of the primary ways that we input clock groups into the tool. And give the user control over that is to be able to take the set clock groups from SDC, and we'll also be supporting the set CDC clock group command that's part of the standard.
Okay, so there's a couple of last questions. So somebody's just asked in the chat if Blue Pearl, because obviously a lot of the techniques here that we've been talking about are very FPGA specific. They apply to ASICs as well. So Blue Pearl is capable of supporting ASICs, Dave?
It is. We absolutely have had ASIC users. I believe there may be some at present. Again, the vast majority of our users for the last several years have been FPGA, but I think the original development of the tool was aimed at ASIC. So it's really a question of what do our users want and need, what functionality do they need, and I would say. Certainly talk to us, and and you can try it out. But the tool was originally developed to work with both, so that would be my answer there. And to the degree there's interest, we can certainly work with you to try and make sure that we can help meet your needs.
So the last one question. Somebody's putting there about talking about CDC and how important CDC analysis is, and hopefully by the end of this webinar, everybody agrees with that. Said that they'd not consider this to avoid the need for proper coding standards and coding peer reviews. And what's your view about this? And I think this ties into the initial part of the Blue Pearl visual verification suite that I talked about a little bit in my demo, where I said we can do linting and structural analysis checks, and we can and the tool's able to do that to help you automate that code review, and has a number of 400 or so built-in checks that can be used to do that linting. But Dave, maybe?
Yeah, I don't remember the number off the top of my head, but yes, it's a large number of checks. I suspect it's even larger than that. But in any case, we do have a number of capabilities. We weren't talking about the linting features particularly today, but that is an absolutely important part of the tool that you get with a basic analyze license. And we also have capabilities such as the management dashboard, which allows you to track the number of violations over time and help focus your code reviews on areas that are needing attention and things like that. We have absolutely a number of things that can affect, can check things like coding style, like checking for certain keywords in your names and so forth. Basically, we have a number of customers that are basically using it to enforce their coding standards and to try and support their design reviews. So we absolutely have features to do that. We just weren't talking about them much today.
Okay, so the absolute last question, I promise everybody, last question just popped in at the top. So CDC never guarantees zero probability of a metastable pass-through, just 1/p, 1/p squared, 1/p cubed, etc. So perhaps it is better to handle the metastable case?
Again, sort of metaphorically, it's like it's possible that the coin lands on its edge and just stays there, but in terms of probability, yeah, you basically wind up with increasing or decreasing probabilities that wind up going to zero very, very quickly, but never quite get there, I'd say. It's always possible, if things were exactly right or wrong, that you could wind up in that metastable state for an indefinite period of time. But it's an exponential decay formula, I believe. So the probability very quickly goes to zero for practical purposes. It's just you can't 100% guarantee it. It's more like 99.99999, however many nines in there.
Perfect. Right. Well, I think we've taken up the hour of everybody. I actually figured we were going to be ending a little bit early, but there's been really great engagement, a lot of really good questions. So please, thank you. First off, thank you everybody for attending. It's been very good. Thank you, Dave, for coming and talking and giving an absolutely fantastic presentation and teaching us all about CDC. We'll make sure the recording's available. Everybody's going to get it. Like I say, everybody's going to get an email that is automatically sent that says here's where the recording is, so you can come and record it. If you want to, please share it with people. That's always good. And we'll make sure it's available via the Eduvo website and very probably the Blue Pearl website, I assume, to make sure people can get the slides and they can watch the tool. But thank you very much for attending. I'm going to wrap it up now, and I wish you all a great day and a great evening. And let's hope you've learned something to keep your designs a little bit safer from CDC as we go forwards.
Excellent. Yes. Thank you all for attending.